After this lesson, students will be able to solve absolute value inequalities. In Part 1 of Section 1.5, we talked about solving absolute value equations. When solving absolute value inequalities, it's similar, but when we have an inequality symbol, we need to remember to flip the sign when setting it equal to the opposite value. For these problems, they'll turn into either and or compound inequalities. When you have less than, like we do in number 1, it's going to become an and compound inequality, which I like to remember as less than. We've also talked about how and compound inequalities are like sandwiches. So for number 1, less than will become an and compound inequality. So x is sandwiched. It is less than 2. X is also greater than negative 2. So I can write it like this so it looks like my sandwich. Negative 2 is less than x, which is less than 2. When graphing this, I would have an open circle on negative 2, open circle on positive 2, and the solutions would be in between. In universal set notation, I would have parentheses, since negative 2 is not included, up until 2, which is also not included. It's more difficult to check our answer for absolute value inequalities because now we're talking about a range of solutions. If we wanted to check, we could choose a number that we know is not a solution, so something not shaded in, like negative 4, and make sure that that does not work. We could pick something that is shaded in to make sure that it does work, and again something that maybe is not shaded to make sure that it does not work. Number 2, the absolute value of x plus 2 is greater than or equal to 1. With greater than, it's going to form an or compound inequality, which I like to remember as great or. So I'm going to separate this into two inequalities. X plus 2 is greater than or equal to 1, or x plus 2, switch the inequality symbol to less than or equal to, and take the opposite of 1, which is negative 1. Now I can solve for x by subtracting 2 from both sides. X is greater than or equal to negative 1, or subtract 2, x is less than or equal to negative 3. For our final answer, we want to write our numbers from least to greatest as we read from left to right. So I would write this as x is less than or equal to negative 3, or x is greater than or equal to negative 1. I do this so that it matches our number line. Where negative 3 is on the left, and I'm shading to the left, and negative 1 would be more to the right, and I'm shading to the right. For interval notation, we're going from negative infinity to negative 3, which is included, and from negative 1 to infinity, negative 1 is included, And if you recall, since a number can't actually equal infinity, we put parentheses by both of the infinities. Number 3. Since it's less than or equal to, this would be a less than, an and compound inequality. So I can rewrite this as a sandwich, where I take the opposite of 2, which is less than or equal to x minus 3, which is less than or equal to 2. And now I have to isolate my x. So I add 3 to both sides, and I get that 1 is less than or equal to x, which is less than or equal to 5. I can draw a number line. Where 1 is included, 5 is included, and we shade in between them for our sandwich. And in universal set notation, we're going from 1 to 5, both are included. So don't forget that absolute value inequalities with less than or equal to symbols become and compound inequalities. Less than. And that absolute value inequalities with greater than or equal to become or compound inequalities. Great or. You try the next 2 questions, pause the screen, and resume when you're ready. Number 1. This is less than, so it's an and compound inequality. I write negative 3 is less than x minus 4, which is less than 3. Add 4 to all 3 parts. I get 1 is less than x is less than 7. In universal set notation, we're going from 1 to 7, not included. Number 2, we have to isolate our absolute value expression first. So we add 3 to both sides. We get that the absolute value of 2x plus 1 is greater than or equal to 9. Since it's greater, it's going to be an or compound inequality. So I can write out 2x plus 1 is greater than or equal to 9, or 2x plus 1 is less than or equal to negative 9. Isolate my x. And write from least to greatest. So my answer would be x is less than or equal to negative 5, or x is greater than or equal to 4. In universal set notation, I'm going from negative infinity to negative 5 included, or I'm going from 4 included to infinity. Pause the screen and try these 2 questions. When you're ready, you may resume. Number 1, less than, will turn into an and compound inequality. Subtract 6 from all 3 parts. And we get that negative 14 is less than x, which is less than 2. In universal set notation, we're going from negative 14 to 2, and they are not included. Number 2, we subtract 4 from both sides before we move on. And now that my absolute value expression is isolated, I can say that 3x minus 3 is greater than or equal to 6, or 3x minus 3 is less than or equal to negative 6. Add 3 to all three parts, so 3x is greater than or equal to 9. X is greater than or equal to 3. Add 3 over here, I get 3x is less than or equal to negative 3. So x is less than or equal to negative 1. And from least to greatest, I have that x is less than or equal to negative 1, or x is greater than or equal to 3. In universal set notation, we go from negative infinity to negative 1 included, or we go from 3, which is included, to infinity. These two questions, pause the screen and resume when you're ready. First, I have to isolate my absolute value expression, so I add 2 to both sides. Now that it's isolated, I can say that 2x plus 5 is greater than or equal to 9, or 2x plus 5 is less than or equal to negative 9. Solve for x. And I write my answer from least to greatest. So x is less than or equal to negative 7, or x is greater than or equal to 2. In universal set notation, we go from negative infinity to negative 7, which is included, and from 2 to infinity. Number 4, less than, becomes an and compound inequality. Negative 1 is less than or equal to x minus 9, which is less than or equal to 1. Add 9 to all three parts. 8 is less than or equal to x, which is less than or equal to 10. And in universal set notation, we're going from 8 to 10, both included. Now we're going to practice some real-world problem solving with absolute value inequalities. We're going to come back to this first question after doing this one, which is simpler, and then I think we'll be able to move on to the more challenging one with decimals. So think about a factory that packages cucumber seeds. The average number of cucumber seeds that they package is 25. However, the number of seeds in the package can vary by 3. Find the range of acceptable numbers of seeds in each package. Now, many students are able to tell me that the range would be 22 to 28 without doing much math or calculations on paper. Because it can vary by 3, we can take our average of 25 and either add 3 to it, so we have 3 extra to get 28, or subtract 3 from 25, where we would lack 3 and have 22. We can also set up an absolute value inequality to demonstrate and solve this. Since we're going to use a variable, we let x equal the actual number of cucumber seeds in a package. We know that the difference between the actual number and the average cannot be any more than 3. And since we don't care which direction the difference occurs, we take the absolute value. Meaning we could have 3 extra, in which case x would be larger than 25, and we'd get a positive answer, where we take the absolute value of a positive and end up with a positive. Or x could be smaller than 25, in which case once we subtract that number from 25, we end up with a negative number and take the absolute value to get a positive number. What this is saying is that the difference of the actual number of cucumber seeds and the average, 25, regardless of direction, has to be less than or equal to 3. This is our absolute value inequality to represent this problem. If we were to solve this now, since it's less than, we create an AND compound inequality and solve for x, and we get that 22 is less than or equal to x, which is less than or equal to 28. And therefore, the range of acceptable numbers of seeds in each package is between 22 and 28. Next question. Pause the screen and resume when you're ready. We're going to let x equal the actual weight. The difference between x and the average, which is 390, regardless of direction, so I take the absolute value, has to be less than or equal to 4. For part B, we find the range by solving this compound inequality and getting that x minus 390 is sandwiched in between 4 and negative 4. Add 390 to all 3 parts, and we get 386 is less than or equal to x, which is less than or equal to 394. And we'll go back to that one question that we skipped. So pause the screen and try it and resume when you're ready. We let x equal the actual diameter. The difference of the actual diameter and the ideal of 90.000 can be less than or equal to 0.008. To find the range, I solve my absolute value inequality. I add 90 to all 3 parts. And I get 89.992 is less than or equal to D is less than or equal to 90.008.